Okay, so we have another example to do. This is actually from Norton's Machine Design and Integrated Approach. Bob Norton was a professor, probably a professor emeritus at the Worcester Polytechnic Institute. And his textbook, Norton's Machine Design and Integrated Approach, is a pretty darn good textbook. I'm thinking about using it sometimes, maybe instead of Shigley. But Shigley's got some features that I like better, but Norton's got some other features I like, but either one. So anyway, this is like a fracture mechanics example that, so I took a steel support strap designed to hold a 60 kilonewton static load is in axial tension, was accidentally saw cut during production and now has a 10 millimeter crack on the edge of it. The strap measures 6 meters long by 60 millimeters wide. I decided to change that to 80 for some reason. Maybe I got the original wrong or something. I don't quite know. But let's change that now, just for your benefit. Where did the mouse go? I lost my mouse, man. Where's my mouse? There you go. There's the mouse. There you go. And I turned it to 80. Whoops, wow. I did a little weird thing. I can't even barely see that. Okay, well, it's going to be 80 millimeters wide by 30 millimeters thick, and is made of steel with a yield strength of 540 megapascals and a fracture toughness of 60, critical, which is critical stress intensity factor, 66 megapascal square root meter. Determine the safety factor of the original uncracked strap based on yielding and its new cracked safety factor based on fracture mechanics. How large could the crack get before it fails? And so let's try to do this. Let's write down the things that we know. This is the fracture mechanics problem. This is like example 3 out of the thing. So this is in tension. They didn't tell us how long this is. We're going to have to presume. Let me see if I get this right. Okay, so it's got a crack right there, and it's in tension. And it's got, what does this say? 60 kilonewtons in it. 60, well, it doesn't need to put both of those on there. But how wide is it? I think I decided to make it 80 millimeters wide. And the crack is 10 millimeters. Or the saw cut, we should say. And it's, it says 6 meters long. That's long. 6 meters, boom. What else here? Let's say the yield strength is 540 megapascals. That's something else that we were told. The critical stress intensity factor, 66 megapascal square root meter. Cool. Anything else we need to know here? I don't think so. All right, so before it does anything, it's going to have an area, a full cross-sectional area of, let's see, I wrote the thickness down, is 3 millimeters. So its cross-section is going to be 80 millimeters. Let me go to meters. So we go 0.08 times 0.003 is its cross-section, which is going to be 2.100 e minus 4 meters squared. So the stress of the thing before it's got the cut in it is going to be 60,000, because it's kilonewtons, divided by 2.100 e minus 4. You do that and you end up getting 285.7 megapascals. So the safety factor for yielding, the yielding strength divided by that stress is going to be 540 divided by 285.7, and so I get 1.89. Okay, so let's go and take a look at our information. Now, I think what happens in our book, he's got a little bit of a different approach, slightly different. But let's take a look here. Let's go to our fracture mechanics and introduction to fracture mechanics. Let's take a look here is the scenario that we're looking at here. So some of the things we need is an H over B, and we also need to have an A over B, right? Where A is the crack length in this. So what we end up finding here is our H over B is going to be okay, so with 6 meters, so the H they have is 1/2 of this length, so that's just 3 meters, and the B, remember, is 80 millimeters, so 0.08. So we get 37.5, which is really big. Remember that this is what we were just looking at H over B. Really, really, really big. Okay. There's also something you should notice, this dashed line right there. That's actually, the dashed line was obtained when bending constraints added, right? Which is to say that, like, when you start cutting this thing off, there's actually kind of creates a bending moment that's going to be put on to this thing. So for the solid curve, there are no constraints to the bending, so it's going to go ahead and bend. Here we could kind of stop it from bending. Right here we could, by the way that we apply the constraints onto the thing. So just bear that in mind. Well, when we so what we end up using is the dashed line on the graph, I think, is what we I ended up doing. And I'm wondering if I did that incorrectly. Trying to see. I think that's fair. The trouble is that we don't have this H over B. This is 0.5 and 1. We see how close they are to each other. I used this graph right in here. Let's take a look at our A over B ratio. Maybe I'll take a look at A over B. So the A over B is 0.01. That's 10 over our 0.08. So it's obviously 1/8 of right there, right? And so let's take a look. And 1/8 is here's 0.1, so it's going to be like somewhere in here. So we have to kind of make a decision about where we would want to place this. I decided to go with the 1.1. I'm not sure if that's the right way to do it. I'm a little unsure. I just think that this dashed line is probably going to be where you would end up being, just considering that we had 0.5 right here, right? And so that's when the H is relatively small compared to the width, but when they're equal to each other, we get this line, and maybe if we just kept thinking of a trend, maybe this dashed line, and we are really close down to there. So it's like a decision that I'm making here, that I've decided that my beta that I would get from this is like 1.1, and I'll even put approximately 1.1. It's 1.12 according to Norton, right? Norton's book. So if that's from that source right there, I think I've made a pretty good decision. So the thing I want to calculate is this Ki, which the equation is Ki times sigma b square root of pi a. Now, this sigma is supposed to represent the stress that's far away from the thing, right? So it's like way out to there. So unlike what sometimes I will do on accident, is I will calculate this being the nominal stress, right? So it's not exactly, I might have actually made a mistake in some other problems that you might see. I don't believe that's correct. I believe what you should do, I don't believe this is correct for that sigma. You should instead put it down there. So the stress intensity that we would have here is going to be that 1.1 times the sigma that I got up here, right? That's just the sigma far away, 285.7, square root of pi, and then I'm going to take my crack length of 0.01, 10 millimeters. And what I get from that is 55.7 megapascal square root meter. And so if I have a safety factor based on fracture, what I want to do is take my KIC and divide it by KI. So we just want to see how we were really measuring how far away are we from fracture. So 66 divided by 55.7, and that's going to be 1.19. So we can see we're much closer to fracture now that we have that cut into it. Now we want to estimate. It says the last part of this was how large could the crack get before it fails? That's a little tough. I think I made this thing. I think I overcomplicated the other part of the thing because I started to use the wrong stress for this. Instead of using the far field stress, I decided to this. I think I could instead just simply go 66. And what I want to do in terms of units is just make sure that this and that are the same units, right? So I could go 66 right here. And I think I can go 1.1. We're going to assume it's the same beta. We'd have to do an iteration after we find this and double check, but we already had kind of a messed up situation where we had to kind of pick that. We didn't have a choice. And so this is going to be my 285.7 and square root and pi, figure out A. So I would say that we have, is that true? Yeah, I think that's going to be fun. So we take a 66, divide 1.1, right? That's easy enough. And then 285.7, and see we've divide through. We want to square that, and then we want to divide it by pi, and I get 0.01404, right? So, and that should be in meters. So A of approximately 14 millimeters is where it would fail due to this crack, or if the crack gets that much larger. Now, I also tried by adjusting this and keeping the same load on it, but now now putting in the denominator the width minus the crack onto the thing. And I got like 13 millimeters, right? So adding that element back into there was sort of an interesting type of twist onto there. But those are the things that I would get into, right? And I mean, those are the answers that I would approach in here for that problem. It's just a simple fracture mechanics introductory type of problem. Try to emphasize that we're using the stress intensity factor compared to the critical stress intensity factor, aka the fracture toughness. Just to get acquainted type of problem. The end.